So welcome from that review. However, we have videos, you can watch all the videos, okay, for a detailed review. It's okay. So let's see how chloric 5 behaves. Now for this one, it's really a powerful oxidizing agent, okay, and it can only do occur in aqueous solutions. So powerful oxidizing agents. Now for the salts, they are more stable, okay, that they can go ahead and occur in solid state. But for the acid, chlorous acid, it occurs only in aqueous solutions. They are obtained by passing chlorine through a hot concentrated alkalis, and the alkalis could be sodium hydroxide or potassium hydroxide. And I hope you still remember this reaction. We talked about it so much. Reaction of chlorine with hot concentrated alkalis. So we shall produce our chlorous, our chloric 5 acid. If it's a salt, in this case we shall form sodium chlorate, okay, and then sodium chloride plus the water molecules. But that is if the acid or the alkalis is really hot and it's really concentrated, okay. Yes. Then with this we shall produce our chlorous or our chlorate. So that's how we can prepare our chlorates. Now you can see in a solution form you have both a chlorate and it's soluble, and a chloride and it is also soluble. So then how are we going to isolate these two, the chlorate and the chloride? It is simple. We shall isolate these two by fractional crystallization. Now what is fractional crystallization? It's a technique that we can use to separate two soluble salts with different freezing points. However, the freezing points are not that, the margin is not big, okay. We base on their differences in freezing points. However, the difference is not that big. So that's why we do fractional crystallization. So how do we do? We dissolve a solution, or we dissolve our solution mixture, like in this case. Remember, it's hot and concentrated. You are reacting it with hot concentrated, so it is hot. So if we know the freezing point of chlorate and we know the freezing point of sodium chloride or a chloride, now the one which freezes before the other, you're going to cool the solution, this hot solution. You will cool it until when you reach its freezing point. So when you attain the freezing point of the one that cools before the other, then it will solidify before the other. And when it solidifies before you attain the freezing point of the second, then you find ways of removing the one that has solidified, okay. Yes, so that's what we call. Now with fractional, that is crystallization. Now fractional, you do it over and over and over again until when you obtain a pure substance, okay, a pure substance. So that's basically how we can prepare the chlorates in a laboratory. So how do they behave? In acidic medium, of course, like how we've said, they are really strong oxidizing agents, okay, and this is their reduction equation. You have a chlorate which is 3 and then minus, and this is aqueous, and then in acidic medium, okay, this is a plus, okay, and then it will give us obviously a chloride, okay, plus our water. So let's try to balance. If we put a 3 here and we put a 6 here, our equation is balanced. Not so? Good. So the equation is balanced, but now what next? They are the charges. So how shall we then balance the charges? This side we have 6 positives, and this side we have 1 negative and 1 negative. So this negative will cancel out with this negative, and then we shall just put 6 negative here, okay, the 6 electrons to cancel out the effect of these 6 positives. And so this is the reduction equation, okay, reduction equation. Maybe if you are reacting it with another compound, maybe, okay, we can say chlorine, okay, iodine or iodide ions, okay. So the iodide ions, they will undergo what we call oxidation. They will be oxidized to iodine, and this is in aqueous solution, okay. And then you balance the equation by putting a 2 here, and then these 2 you add here, the 2 electrons, to balance the charges. So then we shall cancel out this, and then this one remains 3 electrons. So we shall multiply the whole of this with 3. And what you write will be the final equation. Maybe let me write it. With the teaching, you don't take things obvious. So it shall be the chlorate. It will remain as chlorate. Let me write it here because that's where I have space. So you have chlorate, and this is aqueous, okay, and then the chlorate reacts with 6 hydrogen ions, okay, and this is also aqueous, then plus, now 3 times 2, what do you get? You get 6. So plus 6 iodide ions, and this is aqueous. We shall get our chloride, okay, the Cl, which is a minus, and then plus our 3 water, plus our 3 iodine, okay, and this is aqueous, then plus our 3 water. So now if you have this equation and the water is a liquid, you can titrate this liberated iodine with sodium thiosulfate, okay, and then you get the moles of iodine that were liberated, and then from moles of iodine you get the moles of thiosulfate, of chlorate, that reacted from this equation. You don't even need to get you don't need to do this. The equation is the same, okay. So from this equation you can see that 1 mole of chlorate liberates how many moles? 3 moles of iodine. So how many moles of this therefore that reacted? Now depending on the question you can drive it home, okay, and you have the correct answer. So as long as,
excuse me teacher,
yes,
excuse me teacher, how does iodine become aqueous?
Oh, that's some good question. How does really iodine become aqueous? The answer is simple. This iodine that is liberated, it doesn't evaporate out. It remains within the solution form. In fact, iodine doesn't dissolve in water, but because the iodide is going to be excess, okay, then the liberated iodine Okay, it doesn't dissolve in water, but it will react with more iodide ions, okay, aqueous, to form the complex, the triiodide complex. This is the theory, the triiodide complex. So that's why iodine is going to exist in an aqueous form. So when you come and react it with thiosulfate, then the thiosulfate having more affinity for iodine, it will come and knock out the iodine from this complex, and the iodide ions will remain in the solution form. Is that okay? So that's why we write aqueous, not gas. The gas one, the gaseous iodine is the one when you heat, for instance, iodine solid, it will sublime to form iodine vapor. So that's when you put gaseous. But now in aqueous solution, if iodide ions are oxidized to iodine, then it will remain in aqueous solution. So that's why we put aqueous. Have I answered?
Yes.
That's brilliant. That's brilliant. So you should get used with writing these half equations. Write these half equations as much as you can, because they are killer. They are magic bullets. Trust me, you cannot fail any practical question. One, if you know how to write all half equations. Because now you'll be dealing with potassium permanganate, potassium dichromate, or iodine for titration, and some other. They can give you oxalate, that ethane dioic. They will be varying, but trust me, your first practical is either going. Anyway, we might start with a mixture, these simple ones. Sodium carbonate and sodium hydrogen carbonate, sodium carbonate and sodium mix. But apart from that, then you go to these redox reactions, half equation. So if you know how to write these half equations, then I promise the chemistry is going to be cheap. Chemistry practical is going to be cheap. Okay? Because if you can write the half equation, then you can calculate any question. You start with a standard solution, you calculate backwards. Okay? So you get used to writing these half equations. And we have a number you can practice, you can find all of them out, and you write all of them. All of them. Okay? That's brilliant. So it oxidizes iron to iron 3, sulfide to sulfite ions, to sulfate ions, and then iodide to iodine. Yeah, for instance, I wrote this. I've written this. Can you do this? Maybe let me give you half equation for sulfide, and then you proceed and finish. So sulfide, it is SO3, okay, 2 minus, okay, and then plus water. This is a hydrolysis. It is hydrolysis, okay. Then we shall get SO4, okay, SO4, 2 minus, and then plus hydrogen ions. So try to balance the equation. If we try to balance, we are seeing 2 here, so we shall just need to put a 2 here, and then plus the 2 electrons. So this is the half equation for this. Then plus the half equation for chlorate 5, I wrote it for you. Then can't you write the equation? Please write, please write. Let's not take things for granted. How far have you reached? It's okay, you can pause. So like I told you, those half equations, they are really good. And in fact, you have a question here. You can see how it is done. Huh? Such an interesting question. You can see. We have a solution of a Hlorates, and this is a Hlorates 5. However, they have not told you which Hlorates. Okay? It could be a Hlorates, it could be a bromate, okay? Or it could be, or it could be an iodate. So the question wants you to determine, is it an iodate, is it a bromate, or it is a chlorate? So how are you going to determine? You determine the atomic mass, okay? The relative atomic mass, okay, of this Y, and then after you compare from the periodic table. Is it chlorine? If it's 35.5, is it chlorine? If it is, what is the RAM of bromine? I don't know. What is the RAM if you find when it's... So you compare from the periodic table, okay? And find out which one is it. And then you conclude that Y is either a chloride, or Y is either a bromide atom, or Y is an iodide. And the rest is the same. So you can see it contains contains 2.4 grams per liter. This is the concentration, okay, of Y. Now 25 of this solution was added to an equal volume of acidified potassium dichromate. So what does that mean? Obviously the iodide ions must be high. So you're going to you've acidified it, okay? So the other half equation, Y iodate, it is the same to react with. Let me just chop with don't mind about the states. So I'm trying to be quick. So to give us Y ions and then water. So when you try to balance your equation, we shall put a 3 here and then a 6 here and then a 6 electrons. Then the iodide ions, okay, they will give us iodine, okay. And then when we put a 2 here, and then we shall need to put another 2 here. And so what does that mean? You cancel this, so it will be 3, the other equation. Now you have the equation of reaction. Then the iodine liberated, it is titrated with this solution. It is also a standard solution containing 24 grams per liter. This is the concentration of sodium thiosulfate. 5 water. Don't mind. So you can convert. You have the concentration in grams per liter. They dissolved 24.8 grams in 1 liter. But it is sodium thiosulfate, 5 water they have given you. Can't you find a concentration of this in moles per liter? And then from moles per liter, can't you get moles in 25? And then from moles in 25, can't you get the moles of iodine that reacted with moles of thiosulfate in 25 to complete reaction? Yes. If you have moles of iodine, can't you go back now and get moles of Y from the general equation that you saw? Yes, you can. Now, if you can, you have moles of iodate in 25. But the question wants moles, sorry, the concentration is given. They dissolve 2.9 grams, 94 grams of the iodate in a liter. So if you have moles in 25, can't you get moles in a liter? You can. So if you can get moles in a liter, but you dissolved 2.4 grams, okay? 2.94 grams. then it means 2.94 grams contain the exact those moles. Then how about one more? Now if you have one more already, can't you get the relative atomic mass? It means that one mole, the moles contained in one mole, is the moles in in the RFM of Y. Now if you have moles in RFM of Y, can't you get the RAM of Y? You can. Now if you can get the RAM of Y, can't you get the what is Y? If it's 35.5, then the Y is going to be chlorine. I don't know the RAM of bromine. The RAM of iodine is I think in 200 something. So basing on what you've gotten, then you can determine whatever it is. So if you want us to do this calculation, it's okay, we shall do. But I just gave you the hint what you're supposed to do. But if you want us to do this calculation, it's okay, we can do. So suggestions in the chat box. So most people are in favor of us doing the calculation. Let's do. So like always, we start with a standard solution. And the standard solution is this. It has, they prepared this solution by dissolving 24.8 grams in a liter. So what will be the RFM? The RFM is going to be 23 the RAM of sodium times 2. Okay, I hope all of us here know how to calculate. Really, you can't reach senior 5 when you don't know how to calculate the RFM. Then plus 32 the RAM of sulfur times 2. Okay, you close brackets. Then plus 16 times 3, which is 48 the RAM of oxygen. 16 times 3 the RAM of oxygen, and then plus 5 times 18 the RAM of water. Innocent, what is the answer? So you have the RFM. Don't put grams because it's relative. Relative means ratio. Now after getting grams, then you find moles in 100. Okay, so if RFM, please get the RFM. If RFM weighs 1 mole, if RFM, please get the RFM for us. Then how about?
I got 248.
You've gotten 248. So if 248 grams, 8 grams of sodium thiosulfate 5 water contain 1 mole. Okay, contain 1 mole. How about the 24? 24, obviously that's 1. 24.8 grams contain. So give us the answer. It will be this times this out of this, which is 24.8 times 1 out of 248. So what's the answer? 0.1.
0.1.
Moles. So the answer is 0.1 moles. This is 0.1 moles. So meaning the concentration of this solution, this one, it is 0.1 molar because they dissolved 24 grams in a liter. Okay, but of the whole of this solution, if that is the concentration, the liberated iodine required just 25.2 centimeters cubed. Okay, So if 1,000 centimeters cubed contain how much? Contain 0.1 moles 0.1 moles. How about 25 centimeters cubed contain how much? This times this out of this, so it will be 25 times 25.2. Don't forget to include that 2. 25.2 times 0.1 divide by 1,000. So what's the answer? A. This one is I think 0.025.
0.00252.
0.00252 moles. Okay?
52. Yeah.
Okay. Now from the equation, let me write the equation. The equation is going to be 2 thiosulfate ions. This is 2 minus. I hope you can see that. Aqueous. They react with iodine. So we got in this equation from the half equation that we wrote to produce S4 O6 2 minus, and this is aqueous, then plus the 2 iodide ions. 2 iodide ions. So from this equation we can see that 2 moles of thiosulfate react with 1 mole. So 2 moles of thiosulfate from the equation, let me not write, reacts with 1 mole of iodine. Then how about these ones? 0.2 0.0 you should get us the answer 52 moles. They will react with the half of this. So this, let me write, since you want me to write 0.02552, I'm even sweating, times 1 out of 2. So what's the answer? What you're trying to do?
0.0126.
0.00126 moles. That's brilliant. That's brilliant. Now from the equation still, remember how iodine was liberated? We combined the 2 half equations, yes, and the half equation, one was Y. Let me just write the final equation. It is Y3 aqueous, then plus the 6 hydrogen ions aqueous, then plus the 2, actually they are not just 2 but they are 6 iodide ions. Iodide ions aqueous. From this equation then we shall get our Y minus aqueous, then plus the 3 iodine, 3 iodine, and this is aqueous, and then plus plus our 3 water molecules. So that is the equation. So I combined the other 2 half equations. Yes, if you can't get it, I know you cannot write this equation the way it is right now. So for you first write 1 half equation, and then you write another half equation, and then after you combine the 2 half equations. But from the equation, I can see that 3 moles of iodine are liberated by 1 mole of iodate, of our Hlorates. Okay, so from the equation, 3 moles of iodine, okay, are liberated by 1 mole. I'm trying to be economical as far as space is concerned. Reacts with 1 mole of the Hlorates, Y3 minus. Okay, now how about these ones? How about 0.00126 moles? So I'm trying to be economical. If I'm writing tiny words, you forgive me. They react with this times this out of this. So it will be 0.0026 times 1 out of 3. So what is the answer? So we shall have moles. Okay, let me write it here. We shall have moles of the iodate. But see, what's the answer? Please hurry up. You want me to use my head? It's okay.
4.2 exponent negative 4.
Yeah. This is 4.2
Exponent negative 4.
times 10 power negative 4. I was going to use my head because if you divide this by 3, this is 4 and this one is 2. So it becomes 0.0, then 2. This is 0. And this one can't divide, so it's another 0. So that is it. That is it. I was going to use my head. So now, this is 4.2 times 10 power negative moles of the iodate. But the iodate in how much? You see, where? 25 of this iodate solution. It is the one that was added to an equal volume, okay, of iodine. But iodine is, the iodate ions are in excess. Oh, sorry. The iodate ions are in excess, okay? So it is the iodine that is going to determine how much, okay? In other words, the whole of this iodate is going to react since iodine is in excess. So the iodine that is liberated is due to the iodate in 25. And you have seen that iodate, the 25 moles of iodate, the 25 centimeters cubed iodate solution contains how much? 4.2 times 10 power negative 4. So if 25 contain those moles, how about the 1 liter? Okay, so you say if 25 contain 4.2, let me just try to economize space. 4.2, okay, times 10 power negative 4. How about 1,000? Contain how much? This times this out of this. What's the answer? Let's hurry up. You also want me to get this by head.
Zero point 0.0168.
0.0168. Now, the 8 has disappeared. What is wrong with this 8? So, now this is molar. This is the concentration of our iodate. But now, we dissolved how much? 2.94 grams. Okay? And we have discovered that the 2.9, we have 0.016 molar in 1,000. But you dissolve the 2.4 grams in 1 liter. So what does that show you? The 2.94 grams have how many moles? 0.0168 moles. That's brilliant. So if 0.0168 moles weigh 2.94 grams, then how about one more? Why are we doing this? We want the RFM, okay, of this iodate, so that from the RAM of iodate why am I saying iodate? It is a halide. So that from the RAM we get the let's do. So one more is going to weigh how much? This divide by this. Can you get the answer for me? Grams. You want me to get it by head?
75.
Which one?
175.
175 grams. So therefore the RFM, okay, RFM of our iodate. Why am I saying iodate? Our halide, okay, is it sodium halide? Is it, they have not told us which halide, okay, so we are going to suffer. Our halide is going to be 175. A solution of halide 5 contains, and then calculate the atomic. Now they have not told us which halide. Is it sodium halide? Is it potassium halide? We need that. We need that because we can't. There is no halide which exists as Y or minus. So because here you weigh, so there is no halide which exists as this. So we need that. So if let's say it is sodium halide, okay, sodium halide Y3, the RFM is going to be now where can I write? Because if I rub, everything goes. Let me see. We need this. I think we need 175. I think that's what we need. I think even if I rub, we no longer need all this, okay? Yes, I'm going to rub because we need 175 at this stage, okay? Yes, so I'm going to rub everything. You can pause the video. It's okay. I'm going to rub everything. So now, so the RFM of our halide, it is Y or 3 minus. However, we need, is it sodium halide? But is it sodium halide anyway? Is it potassium halide? So we need it, and the RFM is 175. So if we assume to be, let's assume to be sodium halide, so it will be sodium, okay, halide. So the RFM of this, let's assume the RAM of Y to be maybe Y. This one is known, this one is known, so it will be 23, okay, plus Y, because Y is 1, plus 16 times 3, okay, which is 48. The whole of it should equal to 175. So what is this? You get 48 divided by plus 23. This is 71, I think. So Y plus 71. Then we shall get 175. So our y is 175 minus 71. I think the y therefore becomes 104. So you go to the periodic table and find which one has a RAM of 104. Anybody with a periodic table? They are with you? Okay. So for iodine, it is 126 or 127. Anyway, let's round it off. Then for bromine, it is 78, 79. This is bromine. Then this one is iodine. For chlorine, it is 35.5. So this is Cl. So here we assumed if it was sodium, but it can also be potassium. So this question was supposed to be specific. Okay, it was supposed to be specific with which iodate is that. Okay, yes, but basing on the data, if we don't consider sodium, then we shall get this. If you don't consider sodium, the 23, then we shall get 127. But now that one, it is not accurate because you are weighing. Okay, you are weighing. And what are you weighing? You weigh a salt, not ions. Ions occur in solution form. Okay, so it is supposed to be considered. But if we don't consider, let's say you just consider y minus YO3. Okay, it will just be y plus 48. Okay, then is equal to 175. Okay, and so when you take the 48 the other side, okay, take 48 the other side, then we shall get 127. Okay, and which the y is iodine. But you don't weigh this. You don't weigh ions. Ions are in solution form. So the question here, it was lacking something. Okay, it is either sodium sodium y, it is supposed to be given like that. Okay, or potassium potassium halide, it is supposed to be given like that. But anyway, the question says a solution of a halide 5 contains 2.5 grams of a halide 5. Maybe if you consider that, then our answer is going to be iodine. But in practical work, they will give you a solution. They will say you're provided with y, which is a halide. Okay, so dissolve. They will say measure 2.4, dissolve in 1 liter and make a solution. Then they tell you to do all this. Okay, until when and then they will say determine the value of y. So they will say, so they will have to tell you it's either sodium halide or potassium halide or which halide. Okay, because it is what can be measured. I don't know if you are getting my submission. Okay, the halide ions are already, they do occur in aqueous solution. So basically that's how cheap this question was. So let me wait for queries, concerns in the chat box. Okay, and then we proceed. So that was such a simple question. Okay. Let's name. Let's see how we can name. How can we name? We are naming and we are calculating the oxidation state. There is a minus here and there is also a minus here. And we name it, display them once so that. So let's name these ones. Okay. Let's try to name these ones. And then we calculate the oxidation states. I taught you how to calculate the oxidation state of the halogen in such a compound. So you do it chap and post your answers in the chat box. Let's hurry up. Yeah, thanks for the nomenclature. Thanks for the naming. Now, the nomenclature most of you tried. Oxidation states, yes, still most of you tried. But something little was missing. So you want the IU pack. So when you are naming, okay, a negatively charged ion, then that one becomes chlorus. Okay, now this is a chlorus, but most of you wrote this, but you forgot to include the oxidation state of chlorine in the whole of this. It must be there. Okay, yes, so that's where you need to find the oxidation state, and if we don't know, so we shall relate the oxidation state of chlorine to be X plus 2 into the oxidation state of oxygen. The whole of it should be equal to minus 1. So this is X minus 4. Okay, the whole of this should be equal to minus 1. So our X is plus 3. So therefore, this one is chlorus 3. It must be written, put in brackets with dots. So this is what we mean by the IU pack. So chlorus 3 ions. Okay? Yeah, this is what I wanted. Then for this one, now this is a halate. And which halate? Bromine. So it is a bromate. Okay? Now, bromate, then we calculate the oxidation state of bromine in this compound. So we don't know it. Let's call it X plus 3 into the oxidation state of oxygen should be equal to minus 1. Okay? Good. And so this is X into minus 6 should be equal to minus 1. So our X takes 6 the other side, becomes plus 5. So this is bromate 5. Hey, 5 is V. My God. This is bromate 5. Okay. Ions. Because it has an overall negative charge. Anybody who presented that? Fair. Now this one is not an ion. Okay. So when we are naming, we shall name it the way it is. And I'm seeing 2 iodide atoms plus 5 oxygen atoms. So therefore it is tri, not tri, but di. Iodide. Iodide. Nobody named this correctly. All of you are saying iodate, iodate, iodate. This is diiodide. How many oxygens? There are 5. Penta oxide. As simple as that. Diiodide pentaoxide. And what is the oxidation state? It is 2x, because we shall assume the oxidation state of iodine to be x, but we have 2. Then plus 5 into the oxidation state of oxygen. And the whole of this should be equal to the overall charge. And the overall charge in this case is 0. So 2x into minus 10 should be equal to 0. So what is my x? Let's note there on this. My x is going to be plus 5. So that is the oxidation state of iodine in this compound. This one is going to be dichloride. Now where can I write? Okay, let me write here. This one is dichloride. 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 How do we name 7? Yes, 7 is hepta. Hepta oxide. As simple as that. Really? Should this work be hard? So this is dichloride hepta oxide. And what is the oxidation state? Let's calculate it from here. Maybe let me get some different pen. So this will be 2x. We shall assume the oxidation state of chlorine to be x. Oh, okay. 2x plus 7 into the oxidation state of oxygen, which is minus 2, should give us, what is the overall charge here? It's 0. Okay? And so this one is 14 minus 14. We take the 14 this side. This is just simple math, P1 math. We take the x the 14 this side, it becomes positive, divide by 2, so this 7. So our x therefore is going to be plus 7. So are you keen that wherever I'm writing oxidation state, I'm putting the charge? So here it is plus 7, you can see here, you can see here. So oxidation state is written together with a charge. If it's a minus, then you write minus. If it's a positive, then you write positive. Is that really okay to everyone? Is it really good? Yes. Any question before I remove everything here? Okay, so it seems,
Teacher,
yes,
the oxidation states of transition elements.
yes.
You didn't tell us.
Transition elements or halogens?
No transition.
We haven't reached there. But what's wrong with the question? What's wrong with oxidation states of transition elements?
I, I was trying sometime, but confused me.
They do have variable oxidation states. And what confused you? Okay, just have no worries. We shall study transition elements when we finish some topics in physical, and then when we push with organic. Okay, we shall talk about transition elements, and you'll be happy. By that, organic chemistry is also good, and you will enjoy. So basically, that's how we do calculate the oxidation states. So I'm going to rub everything. So you can, there's a question, we have seen the halogens, you can imagine, all of them are forming positive, positive, positive. So why do they form positive oxidation states with oxygen? Can you write science in the chat box? Now one of you has said the answer, and most of you are thinking about it. Yes, when you react these halogens, or when these halogens directly combine with oxygen, now because oxygen is more electronegative than the halogens, then the oxygen is going to induce these halogens. Yes, they are all electronegative, their electronegativities are high, but for oxygen is more electronegative than the halogens. And so that's why when the two atoms combine together, the one that is more electronegative than the other assumes a negative charge. And the one that is less electronegative than the other assumes a positive charge. So that's why among all these oxo acids, all these oxides of halogens, the halogens assumed a positive charge. Why? Because oxygen is more electronegative than the halogens. It will try to attract the bonding electrons. And so, if you attract the bonding electrons, then you induce a positive charge on the halogen. So it ends up gaining a positive charge. Then let's talk about the interhalogen compounds. Now these are molecules where different halogens combine together. For example, you may have such a compound, iodine with chlorine. Okay, is this even 3 or it's 2? Which one is more electronegative? This one. So halogen, okay, the halogens themselves combining together to form compounds. Okay, so for example, fluorine, chlorine, iodine, and they combine them with themselves, okay, to form a compound. No atom of any other element but apart from halogens themselves. So the formula is generally this X, Y, where X and Y are two different halogens, where N can be 1, can be 3, can be 5, and can be 7. Why? Because you've seen that these halogens, the oxidation states are in orders 1, 3, 5, and 7. So they cannot be between. So where X becomes is the less electronegative, and Y is the more electronegative halogen. Okay? And N is always the odd because of the valencies. So most interhalogen compounds are known as binary, whereby they are composed of only two. Okay? Two distinct elements. For example, you may have this iodine with Cl, okay, with a minus, okay. This is iodine monochloride ions. You may have Cl with 3 fluorines. So the one with a high charge is the more electronegative, and so it is the one which assumes a negative charge, and then the other one assumes a positive charge. So what is the oxidation state of chlorine in this? That's obvious case. It is -3. Then here, so those are interhalogens. Let's talk about qualitative analysis, and then we call it a day. And this is some simple work. Let's see how we can confirm in a laboratory that this solution contains iodide ions, this solution contains bromide ions, and this solution contains chloride ions. Now there are two reagents, there are two solutions that we can use here. And the first one is silver nitrate solution. This is actually a confirmatory test. for halogens and red 2 nitrate solution. So with red 2 nitrate solution, if chloride ions are present, then we shall form a white PPT. White PPT, you can see. But if bromide ions are the ones that are present, then you form some faint yellow PPT. Okay, you can see. But if iodide ions are the ones which are present, then we shall form a yellow PPT, you can see. Initially you start with a colorless solution, then you add there another colorless solution, but this is a colorless solution of iodide ions, maybe potassium iodide, and you add there red 2 something, maybe red 2 nitrate. Okay, the solution is going to turn, it is going to form yellow PPT, as we can see. Okay, but for bromine it's pale yellow, not as yellow as this. For chloride it's a white PPT. I think this is common even in O-level work. This is really common. Now that is with red. Now after getting this, to confirm that really you are dealing with a halogen, then we shall use silver nitrate solution, and the same observations are seen. Okay, whereby with chlorine or with chloride ions you get a white PPT, with bromide ion you get a pale yellow PPT, same observations, and with iodide ions then we get a yellow PPT. So basically that's how we shall call it